deals with equilibrium, or more specifically, dynamic equilibrium. So we can think of this in two ways, either physical equilibriums or chemical equilibriums. And I've got two images there that we'll discuss shortly. First of all, it has to be in a closed system, and that's why I have a thermos here. It's representing our closed system. Granted, thermoses aren't 100% closed, and so if we put something hot in there, it'll eventually get cold, or if it's cold, it'll eventually get to room temperature. But for the most part, we're thinking of closed systems, so where no energy or matter can go in and out. So the particles in these physical equilibriums are going to be they're going to be at equilibrium. And what does that mean? It means that if one thing changes, the other thing changes back. So I've got another image here. This one's an Erlenmeyer flask that's capped off. I'm assuming that my temperature around it is going to stay the same. And my water in the liquid form, that's down here, is going to be in equilibrium with the water that's in the gaseous form, or in little gas bubbles above it. And I see in these arrows that if one's going down, another one's coming out of solution for it to be at equilibrium. So the liquid and gas changes are happening at the same rate. So if one goes out, one comes in. If one comes in, one goes out. Heterogeneous equilibrium and occur with with solubility. I'll link to this video so you can take a look at it. But we're looking at, assuming we have something like table salt in a solution. That table salt is saturated, so I can see some salt particles at the bottom. Well, every time one of the salt particles dissolves, another one gets solidified, and so I get those little crystals changing, and over time I'd see a difference in the shape of my pile of salt. So all reactions have the possibility of three outcomes. Either my reaction could go completely to the products, and that's because the products are energetically favorable and have a low activation energy. And here I have an Erlenmeyer flask with some acid and phenolphthalein, and I'm dropping sodium hydroxide into it, forming table salt and water. And I see that pink because I'm getting slightly over the amount of sodium hydroxide, or the base, that's present. So I can't get my reactants back. My second thing is that I can't form any products at all. I can put two things together, and it kind of stays the way that it is. These are energetically feasible, but their energy of activation is too high. Activation energy. That's, if you don't remember, that little A means the activation energy. It's too high. So I've got water there. Yay, water. That water is fine the way it is, but it could dissociate into, or not dissociate, but decompose into hydrogen and oxygen gases. It could happen. It's energetically feasible, but the activation energy is too high, unless I change some of the specifications. So higher energy or higher heat added to it, then it's more likely to happen. My third option is that we can form reactants and products at the same time. This is my equilibrium reaction, and that's where the energy of the reactants and the products are similar. So a reversible reaction is a reaction that does not go to completion. It forms reactants as well as products. The symbol that I use is a forward arrow and a backward arrow. The general form is AB is in equilibrium with C plus D. Now, it could be just one reactant forming multiple products, a decomposition reaction. Or it could be multiple reactants forming one product, a combination reaction. This one would kind of insinuate a double displacement reaction or something like that. But this is just giving us an idea that I have reactants forming products, and my products are forming more of my reactants. If the products are slightly more favorable, I can write it this way, where I've got the top arrow slightly longer than the reverse arrow. And if the reactants are slightly more favorable, I can write it this way, where my reverse arrow is slightly longer than my forward arrow. So chemical equilibrium. We talked about physical before, now we're thinking more about the chemical. It's a reversible reaction that occurs when a system is closed, so there's no energy or matter that can be lost or gained. The reaction is eventually going to reach a point where the forward and reverse reactions occur at the same rate. So I'm forming products at the same rate or speed that I'm forming reactants. This reaction is called dynamic. In the forward reaction, we say form the products, or the stuff that's on the right. The reverse reaction is what's forming the reactants, or the stuff that's on the left. So think about rate. When the reactants are initially placed together, how is the forward and reverse reaction going to relate, and why? If you read through those, you're going to figure out that the answer is D. The forward reaction occurs very rapidly initially, while at the very initial, the reverse reaction is not going to occur. That's because there are no products to start forming more reactants. So that's why it will not occur to start.
Would the following students please come down to the counseling office? Jonathan Pope, Eric Hendricks, Isaiah Pearson, Justin Less, Brody Ryan, Xavier Morris, Tobias Slager, Daniel Lee, Chris Potter, Kepke Hodeling, Sharon Marenga, Zoe Peterson, Tyra Ramsey, Annika Johnson, Pamela Juarez, Ariana Thompson, Tess McQuillan, Kiana Robinson, Claudia Scroggins, Jonathan Ailey, Mohammed Eid, DJ Alexander, Usama Hassan, Hussein Hussein, Keelan Jones, Melissa Clark, Amina Defo, Hodan Dubad, Anjali Goodwin, Mara Hendrickson, and Unita Thomas. Please come to the counseling office.
Okay, here we have some graphs that are showing us how concentration and time relate to where I reach equilibrium. And the point where I reach equilibrium is where my lines are no longer changing in the rate. So my rate is 0, and they have formed equilibrium. They're horizontal to the x-axis. That is the point where I have reached equilibrium. Notice, and this could be made the same way, they could be made differently, but notice what's happening is that my place where they plateau could be different, meaning that the concentration of each is different, or at the end they could have the same concentration. Both of these are showing the same general thing, the place where they form equilibrium, but we just need to realize that equilibrium doesn't mean that they're necessarily going to have the same concentration as the other part of the reaction. Okay, here they're very different concentrations, but the thing that I'm looking for is where they plateau. So dinitrogen tetroxide is a liquid placed in a heated closed system. It's going to vaporize and decompose into nitrogen dioxide. Conversely, nitrogen dioxide is going to dimerize to form dinitrogen tetroxide. That's kind of what's going on here. 2 different vials at different points in the reaction. This is initially, and this is partway or once it's reached equilibrium. So the balanced reaction of dinitrogen tetroxide would be N2O4. And then my equilibrium arrows forming NO2. If I balance that, it'd be 2 NO2s. So what happens to the concentration of the dinitrogen tetroxide as time passes? Well, it's going to start forming nitrogen dioxide, so it's going to decrease in concentration. And it's going to decrease rapidly at first and then more slowly as it plateaus. And why does this have to occur in a closed system? It's because it's forming a gas where they are all gases, and the gases could be going out into the atmosphere, and we wouldn't have those things able to react to form more of the reactants anymore. And we also don't want to change the temperature because it says that it needed to be heated to start with. So we're going to have to keep that consistent as well so that we don't change the rate at which they are changing.